Good evening, everyone. I'm Professor Andrei Zvelindovsky from University of Lincoln in the United Kingdom. Very warm welcome to everyone who came to our Astro-Chat with our distinguished guest, Professor Don Kurtz. Before we start, for those who are new in this Astro-Chat, please remember that you can ask questions to Don by posting them below in a live chat. Also, I would recommend if you could subscribe, push the subscribe button for our YouTube channel. It will help us, but also you will receive timely notifications. I will not tell a long introduction about Don. Those who are new to our channel can look on descriptor where there is a good description about Don, but just mention that Don is a very international person. He's originally from California and then spent quite a long time in his astrophysics research career both in South Africa and in the United Kingdom. Currently, Don resides in South Africa, in Northwest University, and he right now there we connect via this link and talk about astro things. In his career, Don served as Vice President of Royal Astronomical Society in United Kingdom. And in 2022, he was awarded a prize from Royal Astronomical Society for his promotion of astrophysics in his public outreach all over the world. And with that, I'll give floor to you, Don.
Thank you very much, Andrei, and good evening, everyone. I'm glad to be back for another Astro-Chat. It's been a while since we've done one. Let me share my screen with you. So we'll go to the slideshow. And Andrei, will you confirm that you're seeing that, please?
Yes, I see it. Fine.
Right. I've called this comets fiery messengers. For thousands of years, people have been both fascinated by and frightened by comets. They've thought them as being messengers from the gods with fiery tails streaming behind them as they rush through the sky. And what we'll find tonight as we learn about comets is they are not messengers from the gods. The tails are not fiery, and usually the tails are not streaming behind them as they travel through the sky. So having fully debunked that rather nice title for the talk, let's have a look at some comets. Some of you in the audience now, I'm sure, last week or the week before, will have seen this new comet that just reached naked eye brightness last week and the previous week. It has a very big mouthful of a name, Comet C 2023 A3 Su-Chen-Shan Atlas. What in the world is with this naming convention? In recent decades, we've named comets after the people who've discovered them. In fact, for centuries, as in Comet Halley, which we'll come back to. This name here, the C stands for comet. It says the comet was discovered in 2023. A3 means that it was discovered, the A means it was discovered in the first half of January. Second half of January would be B. First half of February would be C, and so on. So it was the third comet discovered in the first half of January of 2023. It was discovered from the Purple Mountain Observatory in China. In Chinese, that's Su-Chen-Shan. And it was discovered by the ATLAS project. ATLAS stands for Asteroid Terrestrial Last Alert System. That sounds pretty dire. The main telescopes are in Hawaii and here in South Africa at the Sutherland Observatory with other telescopes around the world. And that system picks up comets, asteroids just before they're about to hit the Earth and can warn you if it's about to hit your city, stay away from windows or take care of your last affairs if it's about to blow your city away, but it's going to be too late to do anything about it. So these are for relatively small, but still very dangerous asteroids. That's the ATLAS project. Here's a beautiful picture of that comet. We'll call it A3 from last week over the mountains of California. And you'll see that it strangely seems to have two tails. A big one going to the upper left, and then it seems to be a much fainter one going in the opposite direction. And we'll come back to an explanation and an understanding of that in just a little bit. Here's Comet A3 seen from the space station, picture shot by one of the astronauts up above the atmosphere. And just one more practice with the naming. Here's another beautiful comet, was discovered in 2020. You'll see it's F3, so A, B, C, D, E, F. It's the end of March, third comet in the last half of March. And it was discovered by the NEOWISE space mission. WISE was a Wide Field Infrared Survey Explorer, which did its mission and then was repurposed to look for near-Earth objects, which is the NEO, and it too finds comets. And so there's a beautiful picture of this comet from July 2020, seen above Stonehenge, where most of you are in England now. Near-Earth asteroid discoveries, comet discoveries are now being made, well, primarily by missions that are searching for objects that could be of danger to the Earth. And so here's today's latest count of a year-by-year discovery of objects that could be of some threat to us. And you'll see, since it's only October 2024, hasn't built up to the year end. But you can see how the numbers are going up and up. And most of these are projects, both in space and on the ground, that are looking for objects that are of danger to us here on the Earth. And they discover many, many comets. And so you'll find comets named after Linear, which in fact is Lincoln Lab, but that's Lincoln Lab, not Lincoln at the university we're at now. That's Lincoln Lab, MIT, and the US Air Force, NASA in the United States. Pan-STARRS ground-based observatory in Hawaii, NEOWISE space mission, Atlas ground-based telescopes trying to find objects that are dangerous. There's the cumulative number going up. You'll see in the bottom, the red ones down here, these are ones that are pushing extinction level events like the end of the Cretaceous. And there are not very many of those. None of them are on a collision course with the Earth at the moment. Up to 140 meters, 140 meter diameter comet or a rock that hits us is a major disaster. And you'll see that we have found over 10,000 of those in the last couple of decades, none of which at the moment is on a known collision course with the Earth. Here's a NASA movie. I'm going to run this twice for you. That was Comet A3, and it's viewed by the SOHO, the Solar and Heliospheric Observatory, which has been in space for decades now observing the sun. So what you're looking at here, there's a small arm with a disk on the end of it that's blocking the light from the sun. And the streams you see coming out of the solar wind, there's a wind blowing constantly from the sun. And in this sped up movie, Comet A3 has now passed by its closest point to the sun. And if we start that over, now that blast you just saw right there, all those speckles on your screen was a coronal mass ejection, which was aimed at the Earth. And protons and electrons moving at nearly the speed of the light have now crashed into the camera. And each time one of those hits the charge coupled device in the camera, you get one of these white speckles. So that one blasted the Earth. If a coronal mass ejection like that blasts a comet, the comet can brighten extraordinarily very rapidly, and that's not predictable. And so when we're making predictions about how bright comets could be, it can be very difficult to do because it depends on what the sun's up to, and it depends on how the comet interacts with the sun when it passes close. And we'll come back to that again at the end of the talk for another comet that's coming next week. So back to this instrument. It's called LASCO on the Solar Heliospheric Observatory. This circle represents the size of the sun. This is the disk blocking the sun out. These are streamers coming off the sun and the solar wind. And here's a pair of comets discovered by SOHO. It's discovered over 500 of them. The image is sped up, and those two comets didn't make it past the sun. The sun destroyed them. Once more, you'll see them come flying in. This is probably one comet that was broken up by the gravity of the sun, and then you see the two final pieces collide with the sun. Here's a Christmas comet from 1996. Did you see it? That was very fast. The sun ate that one too. Here it comes. And so these comets are being discovered by many missions, and the SOHO mission, as I said, has found over 500 of them. Occasionally, people still find comets and get them named after them, but primarily it's these big missions that are searching the skies for objects that could collide with the Earth. If we look historically, comets are in history going back right to the beginnings of history. When Julius Caesar died in 44 BC, of course, he didn't die of natural causes, as you know. He was assassinated. The next emperor, Augustus, declared that the comet that was seen was Julius Caesar's soul. And the Senate declared Caesar to be a god. That is divine Julius, you see here. And Augustus had minted a coin, which you see here in the lower right, with divine Julius in Latin written on it. 1,500 years later in Mexico, when Hernandez Cortez and his conquistadors attacked Tenochtitlan, now Mexico City, the emperor was Montezuma II. And one of the stories, there are many and nothing's absolutely certain about why Montezuma allowed the conquistadors into Tenochtitlan, but this painting here is supposedly of Montezuma observing a comet over the great volcano, 5,400-meter volcano just outside Mexico City called Popocatépetl. And the painting, that doesn't look very realistic for a mountain, but there's the real mountain on the right. And it's a huge live volcano, and you see the artist didn't do too badly there. So again, historically, there's another case where possibly Montezuma, having seen a comet at some time, thought that it was a sign that he should cooperate with the conquistadors, which was a big mistake. That led to his death very quickly thereafter. Kirch's comet of 1680, also known as the Great Comet. Here's a painting of it over Rotterdam. And this was a very important comet historically. 5 years before 1680, the Royal Greenwich Observatory was founded just outside London in Greenwich. And the first astronomer royal there, John Flamsteed, observed that comet. And it appeared there were two comets that year. There was one seen coming in towards the sun, and then later there was another one seen going away from the sun. And Isaac Newton, through his friend Edmund Halley, got the observations of Flamsteed. It didn't credit Flamsteed, but Newton correctly plotted that great comet of 1680 coming in towards the sun, and then picking it up again from Flamsteed's observations going away from the sun, found it was on a parabolic orbit, which in this case is a very, very long ellipse. It was obeying Kepler's laws, very important, as Kepler had only just invented those laws in the early 1600s. And so this was proof that comets obeyed Kepler's laws, and that these two comets that we're seeing were one and the same comet. Now, Edmund Halley was a contemporary of Isaac Newton, and Halley's name is not certain how it's pronounced. If we look at the spellings from his time, it's spelled Haley, Halley, Hawley. When I was growing up in the 1950s in the United States, I was waiting for Halley's Comet to come back. I was born in the year 1948, and Halley's Comet at that point was at its most distant point from the sun in its 76-year orbit. And so throughout my childhood, I knew about it and was waiting for Halley's Comet to come back and pass close enough to the sun to see it in 1986. So we in America called it Halley. In England, it's called Halley. It's not absolutely certain how Edmund Halley himself pronounced his name, but in America, because it was pronounced Haley, well, there was a rock band then, very clean-cut group, Bill Haley, and he called his band Bill Haley and His Comets, obviously after what Americans called Halley's Comet. Edmund Halley was, I put, quote, friend of Newton. Newton really didn't do friendship through his entire long life. He didn't have what you and I would consider to be a friend. Newton's great publication was his Principia, his Principles of Natural Philosophy, in which he laid out his three laws of motion, his law of gravity, in which he derived from first principles Kepler's laws of motion, and Newton helped push that through to publication. Following Halley having seen that the comet of 1680, the two comets were the same comet, Halley then discovered that the historical comets' orbits, which were known, 1531, 1607, and 1682, all had the same orbit, and he correctly deduced that they were the same comet, and that's the one we now name after him. We know that Halley's Comet has been orbiting the sun probably for about 16,000 years now, and it's certainly seen in historical records going back more than 2,000 years. Edmund Halley himself predicted that the comet would return in 1758, and it did. He was no longer with us, but that was a success. For its next 76-year orbit, celestial mechanics was developed to the point that the time of its perihelion, or closest passage to the sun, was predicted within days, and the comet obeyed that, so we knew that the celestial mechanics theory was working well. The next passage in 1910, we had photography, and we allowed the first astrophysical study of the comet with photographs of it. 1986, the Giotto spacecraft flew right through the coma of the comet, I'll show you that, and got a direct look at the nucleus. And I would predict, not for sure of course, but I would predict in 2061, we'll probably land on the comet and stay with it thereafter with a mission that rides on its surface. Historically, in the 1600s, here's a famous painting by Giotto of the Christ child and the adoration of the Magi. And there's Halley's comet in the background there. It passed in 1301, and Giotto would have been aware of that, and he's taking that to be a sign of the birth of the Christ child. So in this case, it was thought the comet was a good sign. 1066, Halley's comet was then thought to be a dire omen for both the English and the Normans, but after the Battle of Hastings, when the Normans won, it was realized that it was a bad sign for the English, and it was a bad sign for Harold in retrospect. So the comet was taken to be some sort of sign from the gods at that time. It can be found in the Bayeux Tapestry. The Bayeux Tapestry is over 70 meters long. You can still see it in a museum, Bayeux in France. It's only about 50 centimeters high, but 70 meters long. And in one section of it, here are people on the ground pointing at the comet. This is Halley's comet. And the inscription reads, Isti mirant stella, or they marvel at the star in this case being the comet. There are the first photographs from 1910. The comet is moving, and the telescope has tracked it. And so keeping the comet still in the photograph has led to the stars apparently having tracks here, and that's what these lines are, the moving stars staying fixed to the comet. There was another great comet in 1910, which was even brighter than Halley's comet. Halley's comet was April-May. The great comet of 1910 was in January. And it's pretty clear that many people who saw Halley's comet in 1986, but who could remember the comet of 1910, so these people who would have been children in 1910, probably were remembering the Great Daylight Comet from the beginning of the year rather than Halley's comet. There was hysteria in 1910 in the US. Here are just some headlines from 3 US newspapers, New York, LA, and Chicago. Comet to bounce off the Earth today. See comet, then die. Several driven insane, others commit suicide. And you can see here, there were 7 suicides, 5 committed to asylums, 2 murders, 5 accidental deaths, 1 murder confession, and 1 hoax of a virgin sacrifice. Even in 1910, people were frightened by comets. And I suspect even today, not anybody in this audience, but there are people around who think they're still mystical and mysterious and are frightened by them for mystical reasons. Now, we're going to find out there are reasons sometimes to be frightened by comets, but there's nothing mysterious or mystical about that. We'll see the reality in just a few moments. There's a picture of Halley's comet in 1986. It was a bit of a fizzle. We told the world that the best time to look at it was in April of 1986, when it would be at its best position to have its longest tail. And it didn't do much in April, but in March of 1986, I was at the telescopes at the observatory here in South Africa, and there was a coronal mass ejection from the sun that blasted it, and it had a great tail. I really had a good view of it in March of 1986, but we had told you, the public, don't look till April, and I think an awful lot of people missed it because of that. The Giotto mission had gone out long before its closest passage, and here's a real picture from that mission. We'll see in just a bit when the comet gets close to the sun. The comet is a dirty snowball. It's made of rock, but with a lot of ice, and when it gets close to the sun sublimates the ice from a frozen state to gas, water vapor. That water vapor blows out as geysers, blowing jets off the surface of the comet. If you could get onto the comet Halley and ride on the surface, you would weigh something like 5 grams. It is so tiny, there's very little gravity, and so these jets of water vapor blasting off the comet easily blow away rocks and dust and dirt. We were worried that the Giotto mission would be completely destroyed flying through the coma, this material around the comet. It did survive that, but of course the camera lens was badly damaged by it. But there's a picture of Halley's comet itself. It's about 8 kilometers long, it's oblong in shape, and here's the material being heated and coming off the surface and then being blown back into the tail by the wind from the sun. So here's an orbit of Halley's comet, schematically. At its closest approach, it passes closer to the sun than even Venus. At its most distant, it's out beyond Neptune, and it is right now out at nearly its most distant, where it also was the year I was born. It takes 76 years to orbit the sun. Next month, I will be 76. And so I have now lived through one orbit of Halley's comet, from its most distant to its most distant. There's another very famous American who also had a life that coincided with Halley's comet, and that was Mark Twain. And Mark Twain was born November 30th, 1835, 2 weeks after the perihelion of Halley's comet. He said, "I came in with Halley's comet. It's coming again next year. The Almighty has said, no doubt." Now there are these two unaccountable freaks. They came in together, they must go out together. He died April 21st, 1910, one day after the comet had once again reached its perihelion. So within just a matter of a couple weeks at the beginning, a day at the end, Mark Twain's life exactly coincided with two perihelion passages of Halley's comet. Here's an artist's impression of the formation of a solar system. When our sun was born 4.65 billion years ago out of a cloud of gas and dust in the Milky Way, as it collapsed and became denser and denser, it spun faster and faster, and still it spun off a disk of material. That disk orbited about the sun, and in the disk, dust particles collided to make small rocks. The small rock collided to make asteroids and comets. Far from the sun, out where the big planets are, like Jupiter and Saturn, it's cold enough that there was plenty of water ice in the rocks. In closer, the asteroids, like in the asteroid belt between Mars and Jupiter, it was too hot, the water vapor was blown away, and those are largely just rocks. But the far solar system, they formed into comets, dirty snowballs. And then those rocks, interacting largely with Jupiter, but with some of the other large planets, were flung about. Some of them flung into the sun, where they would be evaporated and destroyed, but many, and when I say many, let's say about 1 trillion, were flung out into the outer solar system, to the far reaches of the solar system, where they still are. And that's where the new source of the comets come from today. So here is an artistic impression of the solar system with the sun at the center and the orbits, Mercury, Venus, Earth in here close. And then far out into the solar system, there's a belt in the plane where the planets are called the Kuiper Belt, after Gerard Kuiper, who first found out that this exists 1953. He brought that to the world's attention. Pluto is one of the objects from the Kuiper Belt. We used to call it a planet. It's not. It's just the largest of the Kuiper Belt objects. We've now discovered many objects out here in this belt, and they are icy asteroids. If something would cause them to come close to the sun, they would evaporate their surfaces and they would turn into comets. But the vast majority of comets, perhaps 1 trillion, are in a cloud called the Oort cloud, after the Dutch astronomer Jan Oort, who first hypothesized this cloud must be there. And they're in a spherical distribution because Jupiter has just chucked them out in all different directions. They orbit about the sun up to a distance of perhaps as far as a light year. And so over tens of millions of years, as the sun orbits about the galaxy, and other stars may pass closer to us, they could pass close enough that their gravity perturbs these objects far in the solar system. Some of them get pulled off and completely escape from the sun's gravity. Others are slowed down a bit and they fall into the solar system towards the sun. Now this will take 50,000 years. They appear in the inner solar system, whiz by the sun, and then out they go again to the far reaches with an orbit that will take about 50,000 years. That's the case for Comet A3. If some of you saw that last week or the week before, it's not going to be back for about 80,000 years. It'll go back out into the Oort cloud. Now, those comets can come from any direction. They don't orbit in the plane of the solar system. They can come from the north, the south. They can go backwards. They come from all directions out in this great Oort cloud of perhaps 1 trillion comets still gravitationally bound from the sun and orbiting the sun. If one of those comets from the Oort cloud, when it passes in the inner solar system, passes close to, say, Jupiter, the gravity of Jupiter and the comet, along with the gravity of the sun, can perturb the orbit and cause that comet to go into a very short period orbit. Halley's comet's a case of that with only 76 years. So here's a comet called Churyumov-Gerasimenko. We're going to meet that again in just a few minutes. In its 6.5-year orbit that takes it out beyond Jupiter and then in closer to the inner solar system, a bit outside of the planet Earth. A comet with a larger orbit, like Halley, taking 76 years, goes out beyond Neptune. Those are both Kuiper Belt comets. But then comet sighting Spring from 2013 has an estimated period of millions of years from the distant Oort cloud. Its orbit's completely tipped to the plane of the solar system, and in it comes from the far distant solar system around the sun, and now it's gone, not to come back for millions of years. Interestingly, just recently, we've discovered a comet that came from outside the solar system. This comet must have been flung out of another solar system and came from another star. It's the second interstellar object. The first one was an asteroid, not a comet. This one was a comet, Borisov, and in it came 2019 on what we call a hyperbolic orbit, moving so fast that it's clear it's not coming back. It's not gravitationally bound to the sun. It came close to the sun, sun's gravity bent the orbit, and out it goes, never to come back again, an interstellar comet that has passed through our solar system. So here's how a comet works. Here's, for example, a comet like Halley's Comet. When it's at its most distant from the sun, it's cold out there beyond Neptune, the ice is frozen, and basically it's the big dirty snowball. But as it comes closer and closer to the sun, the heat from the sun will begin to cause the ice to sublimate, go directly from solid to gas. That will then form a gaseous coma around the comet, which gets bigger and bigger as the comet gets closer to the sun and it gets hotter. And finally, when it gets close enough to the sun, the wind from the sun, which you saw in those movies I showed you earlier, always blowing from the sun, blows the comet's tail away from the sun. And so when a comet's coming in towards the sun, indeed the tail's following it, but as the comet comes around the sun, the tail blows away from the sun. And when the comet leaves the solar system or goes back out into the outer solar system, it goes tail first. The tail doesn't follow the comet. It points away from the sun. Now, there are two types of tails. The gas that comes off the comet's very light, and the wind from the sun can blow that tail straight back. But the little tiny bits of dust that come off are heavier, and the wind from the sun's not strong enough to blow them, but light itself exerts a pressure, and the pressure of the light from the sun pushes the dusty tail back, but because these particles are heavier, they tend to go into their own Keplerian orbits. And so that tail is bent with respect to the gas tail. And so if you imagine that when we looked first at Comet A3 a little while ago, it seemed to have two tails. Well, from the view in the Earth closer in looking out, we could see one tail in one direction and one in the other direction. They really were both pointing away from the sun, but they looked like they were opposite us from our perspective. Big rocks get blown off the comet, and so orbiting in the comet's orbit are huge chunks of rock, broken bits of comet that stay in the orbit and then orbit about with the comet as the comet, each time it passes the sun, is more and more destroyed until finally the comet is no more. Far into the future, thousands of years from now, Halley's Comet will be gone. The sun will completely break it to bits. But those bits continue to orbit the sun. And for quite a few comets, the Earth actually passes through the comet's orbit. It does that at a certain time of year when the two orbits collide, like in the picture right here with these two. And at that point, when all this debris from the comet rams into the Earth's atmosphere, we get a meteor shower. And because the comet's only a few kilometers in size, and the Earth's 6,371 kilometers in radius, all the meteors from a cometary meteor shower seem to come from a single point in the sky. So here's a comet from 1996, Mach-Holtz. It's got a period less than 6 years. And in 1996, here with the LASCO instrument, again blocking the sunlight, there's the wind from the sun. And here's multiple exposures of comet Mach-Holtz coming in. And watch how the tail turns and always points away from the sun because the solar wind is blowing it. 6 years later, when Machholz came back in 2002, it's now going to come in on this side here when I run this movie for you. Let me give you a few other explanations. That circle is, again, that's where the sun would be. This is the disk blocking out the sun. This thing here is the arm holding that disk in the telescope. That's the planet Venus, and Venus is so bright that its light is spilling over on the charge-coupled devices, and so this long streak you see here is an artifact. It's just the electrons in detecting the light from Venus have supersaturated, and they've spilled out along one of the columns in the charge-coupled device. All the dots are stars, and as we watch the movie, they'll move slightly because the Earth's moving about the sun. Our perspective is changing. Comet Machholz will come in from the left. There's a coronal mass ejection, but you'll see the wind blow the tail away. And there it is going tail first as it goes away from the sun. And there was a big coronal mass ejection too. So the gas tail's blown away, the dust tail is pushed away by the pressure of light, and there you can see the two tails. These tails are not fiery. They're reflecting sunlight, and in the sense the gas tail is made to glow by the sunlight. But the title of the talk, Fiery Messengers, they're not messengers from the gods, you can see that. They're astronomical objects, and the tails are not fiery. So it made a nice title, but it's not really what the comets are about. Here from 1910 is a historic set of pictures from April through June of 1910, showing you how the tail of Comet Halley changed with time as it was moving around the sun and the activity on the sun changed. There was a mission called Deep Impact, which on the 4th of July, NASA chose that to be on the American Day of Independence, with a 364 kilogram impactor smashed into this comet, created an explosion which blasted stuff off the surface of the comet, and that gave the chance for astronomers on the ground with telescopes to look with their telescopes and see what the material under the surface of the comet is made out of. There was water vapor there was rock, there were organic compounds. Very interesting that you can have organic compounds in these comets. And here's the actual picture of the impact and the explosion that was caused by that Deep Impact mission. Well, Deep Impact mission is related to Hollywood. Steven Spielberg and others decided to make a movie about a comet that's going to collide with the Earth. It's going to cause an extinction level event and wipe out humans. So brave astronauts go out and land on the comet, explode a hydrogen bomb, but it only breaks the comet into two, and both of those are headed for the Earth. So the astronauts on a suicide mission sacrifice themselves to blow one of the bits into pieces, but the other bit still hits. And comets can still hit the Earth. If they hit the Earth, it's like asteroid impact, and these are potentially extinction level events. Let's just for the fun of it watch the trailer of Hollywood's version of what it would be like if a comet this size, a comet the size of Halley's Comet, actually collided with the Earth. How realistic are tsunamis that size? They're actually very realistic. All right, that was Hollywood hype. But the asteroid that hit at the end of the Cretaceous 66 million years ago in the Yucatan Peninsula of Mexico produced a tsunami that traveled 1,000 kilometers inland in what is modern-day Texas. And so realistically, if we get hit by a big comet like that, it's the kind of thing that could happen. We do care. And so we're not only tracking these comets, but we're learning as much as we can about them because of their danger, but because of the incredible information they carry about the birth of the solar system. The Rosetta mission went out and landed on that comet orbit I showed you earlier of Churyumov-Gerasimenko. Here are the various complicated orbit that mission went through. It got multiple gravity assists passing by the Earth and Mars. This is a cheap way for us to get a mission out into space without having to put lots of fuel on it. Once we get it out there, if we have it pass by planets, we can use their gravity to slingshot it and get the energy from the planet, save ourselves some money, save ourselves some payload. And so it eventually arrived 2014 at Churyumov-Gerasimenko, and it put a lander down on the surface of the comet, 12th of November, 2014. Here from that mission is the real picture of the surface of that comet. It's kind of a double comet with a waste there. There's one of the jets coming off the surface from the sun sublimating the ice and turning it into gas, which is blowing off the surface. Again, I did the calculation earlier just before the talk. If I were standing on the surface of that comet, I weigh 80 kilograms here on the Earth, I would weigh 5 grams on the surface of that comet. So even that blast coming off the surface there would blow me off the surface and out into space. It'll blow big rocks away too. The little Philae lander came down near this cliff, and unfortunately it bounced when it hit the ground and it went into a shadow. And because it was in the shadow, solar panels couldn't pick up any sunlight to keep its batteries going. And so there was very little transmission from it. We didn't get as much information as we would have liked. But the importance, these comets coming from the Oort cloud are made of the stuff the solar system was made out of 4.65 billion years ago. By studying the comets, we learn more about how our solar system and our planet Earth formed. When the comets pass close to the sun, the gravity from the sun can not only cause stuff to be blasted off the surface, it can cause them to break up completely. This was Comet Linear back here in August of 2000. And Linear again is Lincoln Laboratory, Near-Earth Asteroid Research Project, Lincoln Laboratory in the United States, not at Lincoln University where we are now for this talk. And so when those bits get broken up, they continue to orbit the sun, and if they happen to cross the Earth's orbit, we get a meteor shower. And so there's a nice picture from China, a young couple sitting on a rock, somebody taking a time exposure of the Leonid meteor shower, November 2022. Those of you who look closely will see the Orion constellation here. There's the Belt of Orion, Betelgeuse, Rigel. There's Aldebaran in the face of the bull. There are the Pleiades. Sorry, there's Aldebaran. Arcturus up here. There's Aldebaran. Down here is Sirius. And these Leonids, every 33 years or so, can put on a pretty spectacular show. Back in the 2000s, I saw a very good show from our observatory up in Preston, in Lancashire, but nothing like the famous 1833 meteor shower. And there's an artist's impression of the Leonid meteor storm of 1833. It was estimated that there were 50,000 to 150,000 meteors per hour for a while during that meteor shower. What a sight to see. Of course, people then didn't know what these were, and they were terrified by the entire event. This is a light curve from the Transiting Exoplanet Survey satellite. This is the main mission that I work on now for my own work on pulsating stars. But this light curve is a very bright star, Beta Pictoris, and it shows the dip in light when a comet has passed in front of the star. There's the main part of the comet, the head passing in front of the star, and then the tail, which is stretched out, gives us this long stretched out recovery as the tail goes in front of the star. And on the right, there's actually a theoretical prediction from quite a few years before about what a comet passing in front of a star would look like. And you can see that the people who did the prediction got it right. And so we have seen comets orbiting about Beta Pictoris. There's an artist's impression. It's a very young star with still a big disk of material around it. We can see in the infrared, and we occasionally see a comet pass in front of the star. Something has dug some comets out of some star system like that, and that's where Beryasov, that we saw a little while ago, came from, that interloper from the interstellar medium that passed through the solar system a few years ago. Now, there's another comet around. The one that just went by, A3, is now too faint to see with your naked eye, but there may be another one next week. I'm sorry to say, when I made the talk very recently, it looked like it was a good chance. Probably not now. It will reach perihelion in 4 days' time, its closest point to the sun. And then as it passes past its closest point, starts to move away from the sun, there were some predictions, even a couple of weeks ago, that it would become brighter than Venus, much brighter than Venus. Unfortunately now, the reason it's getting this title, Headless Halloween Comet, in the news, is that it kind of looks now like that it may have already been broken up by the sun. And so there's a news item from just earlier today. Headless Halloween Comet could already be doomed. While some are hoping for a bright Halloween comet next week, astronomers say the speeding cosmic snowball has already broken apart. Well, stay tuned. If this thing gets bright enough to see with the naked eye in 4 days, in a week's time, not 4 days, that's perihelion, next week around Halloween, you'll see it in the news. Make sure you get out there to see it. Thanks for your attention tonight. Let's go on to our question time.
Thank you very much, Don. Fascinating talk as usual. We have audience today, just to mention, stretching from San Diego to north of Kazakhstan. So it's really quite an extension. And there is a question from Jamie Fernandez Atkins. Why are we spotting more comets? Are we just getting better at detecting them?
Yes, Jamie, we're better at detecting them. When I was young, comets were found by people, usually amateur astronomers, with small telescopes who would study the sky just looking for something that wasn't there the night before. You know, if I take you back a couple centuries, the famous Messier objects, which was a catalog by Charles Messier of a little over 100 of the most interesting fuzzy little things in the sky, including this globular cluster behind me here, he made a catalog a couple centuries ago of all the fuzzy things in the sky that weren't comets, so that when he was searching for comets with his little telescope, he wouldn't keep mistaking these nebulae and star clusters for comets. And so the amateur astronomers would just be searching for a comet, hoping to discover one, and then becoming famous because it was named after them. That happened. The best comet I ever saw was early 1970. I was still an undergraduate in San Diego, and Comet Bennett was beautiful, absolutely beautiful in the morning sky with a huge tail stretched out across the sky. Jack Bennett discovered that with a small telescope here where I am now in South Africa. Became famous. Now, if you discovered a comet that was about to hit the Earth and cause us to become extinct, would you want it named after you? That's another question. But nowadays, they're being discovered by these huge surveys we're doing to try to find all the near-Earth objects that could be dangerous, and also just to study comets in more detail for the interesting astrophysics for the formation of the solar system. And the amateurs really don't get a big chance to discover them before these other telescopes find them now.
Thank you. There is a question from AC from San Diego. Surprised you did not mention Heaven's Gate and no less Comet Schumacher-Levy 9. I've been totally amazed that X-ray have been detected from comets. Do this influence the gas composition of the comet?
Okay, AC, there were a whole lot of things. Anyhow, greetings to you in San Diego. There were a whole lot of things in that statement you just made. Heaven's Gate, you mean the suicide cult? Remember, I'm trying to give you only a 30 or 35 minute talk, so I can't cover everything, and that one I'm going to stay away from. Comet Schumacher-Levy was a comet that passed by Jupiter to where Jupiter actually captured it in orbit about Jupiter, caused it to break into bits. The biggest bit was 2 kilometers in size, and those smashed into Jupiter's atmosphere with incredible explosions that we saw from with the Hubble Space Telescope. And I could see the scars on Jupiter with my telescopes here in South Africa at that time, back in the 1990s. And so Shoemaker-Levy was a good example of what happens when one of these comets hits a planet. In that case, it hit Jupiter. Now, there was something else in your question there. There was
about X-ray detected from comets.
Yeah, go ahead.
And do they influence the gas composition of the comet?
I don't know the answer to that, AC. I'll look it up later. I'm not familiar with X-rays from comets, sorry.
Okay, there's a question from Mika Rollins. Very interesting talk. You say comets are made of water, although probably unknown.
Sorry, is what unknown? Repeat that.
If it's made of water, are we talking as is H2O?
Oh, yes, the answer is they're mostly made of rock, but there's plenty of water mixed in. And yes, that is H2O. That's water ice, as you know it, but it's very, very fluffy. It's even fluffier than powder snow. Remember, there's almost no gravity. These things are tiny. The surface of the comet's also made out of fluffy rock. And so the comet's only barely held together by its gravity, but yes, that water is H2O. And we don't know for sure where the water on the Earth came from. When we calculate how much water is in the asteroids that collided to make the Earth, the water would have come out of volcanoes with volcanic explosions. Water still comes out of volcanoes. That doesn't seem to add up to be enough to account for all the water on the Earth. And there is a conjecture that a good part of the water here on the Earth came from cometary collisions with the Earth when it was young, bringing that water in from the colder parts of the outer solar system.
Okay, thank you. There's a question from Timur. What would you say is the best course of action if we do discover a comet heading to Earth?
Okay, Timur, that problem is being dealt with in trying to deflect, push to the side, either an asteroid or a comet. To do that, you need to find it early enough that you can go out and get it long before it would hit the Earth. Because if it's 8 kilometers in size, it's going to be really hard to give a push. But if it's far enough away, you only need a little push, and you can make it miss the Earth. And just a couple of years ago, we had the Double Asteroid Redirect mission, DART, and it smashed a 65 kilogram projectile into the surface of a small double asteroid and changed the orbit of that little asteroid successfully. I did a previous Astro-Chat on that. And interestingly, the material that was blasted off the surface, is actually coming to the Earth. And there is going to be a meteor shower from the material that our double asteroid redirect test mission knocked off the surface of that little asteroid. It's going to come here and hit the Earth, and we're going to get a human-made meteor shower in a couple of years. Stay tuned on the news for that. And so the idea is to go out and give a nudge to whatever might hit the Earth. And if it's very big, you just have to get it early, give it a little nudge and make it miss the Earth. The big ones are pretty easy to see. We know where everything is out there that might hit the Earth in the foreseeable future that's kilometer size and bigger. We've picked those up. The things that are 140 meters in size, there's some of those we don't know about. That's what the Atlas project is about. And it's not about finding them so we can push them to the side. It's finding them a few days before they
connection issue. If we can try to get Don back into our room.
I hope they are.
Yeah. Okay. Don, yeah, we're happy you're back. What happened?
To everybody who's listening, my Wi-Fi failed, and it took me a moment to realize what I needed to do was to use my telephone. And so I'm now connected through my telephone. I hope I've got enough data to keep us going for 10 minutes. Probably do.
Okay, let's go with questions before connections. Halley is asking, if comets are slowly destroyed each time by passing the sun, is the number of them diminishing?
Oh, the answer to that is yes, but by a tiny amount. You look at the numbers of comets that are discovered every year. We discover dozens of new ones every year that have come in from the Oort cloud. But you remember the number that we think is in the Oort cloud is of the order of 1 trillion. And so if you're losing 50 comets a year, and there are 1 trillion of them out there, well, in 1 billion years, you'll lose 50 billion. You've still got 950 billion left if there's 1 trillion of them out there. There's no lack of comets. So yes, the number, well, in fact, if they're coming from the outer solar system, they have to pass many times too. And each pass takes 50,000 years. So no problem. We're not going to run out of comets anytime in the near future.
And kind of a related perhaps question, asked again from Timur, what happens to a comet's name in case it gets broken in 2 or more pieces?
Oh, good question, Timur. I don't know, and both pieces keep orbiting and we can watch them. I suppose we must call them A or B, but I don't know the answer to that. Well, actually, in the case of Comet Shoemaker-Levy, which was broken into lots of pieces, those pieces were called A, B, C, D, E, F, G. G was the big one. And so there's your answer. They just get letters.
Okay, thank you. Then Marisha Muccelli asking, can comets form planets or would they be considered failed planets?
Oh, neither one, Marika. They're way too small to be what we would call a planet. We've demoted Pluto because it's so tiny. Pluto is smaller than the moon. And so our smallest planets in the solar system, Mercury and Mars, they're half the size of the Earth, whereas the comet's the size of Mount Everest. And so comets crashing into each other could possibly form bigger rocks. That's how planets formed in the early solar system. But there are not enough of them left now. There was a lot more material for planet building when the solar system was forming. We can see disks of material around other stars now with our radio telescopes where planets are forming. The comets are not close enough, the collisions aren't often enough that they could now form planets. And we wouldn't call them a failed planet. They're way, way too tiny.
Okay, then I see John Bass is asking, what happens if a comet passes through the asteroid belt?
Oh, probably nothing, John. Although the asteroid belt looks crowded, if you look at a map of where all the asteroids are, they're really quite tiny. And if you consider all of the space missions that we've sent out past Mars to Jupiter, Saturn, Uranus, Neptune, and beyond out of the solar system, the Voyagers, the Pioneers, Cassini, Galileo, all of those missions passed through the asteroid belt, and none of them hit anything. And so even though there are thousands of asteroids there, it's still mostly empty space. And so comets coming in through there too are unlikely to crash into things. Well, the tails will hit things, but of course the tails are just thin gas, and whatever things pass through the tail is fine. Halley's comet tail, actually, the Earth passed through it in 1910. It's just a thin gas. But no comet has been known to crash into an asteroid going through the asteroid belt yet. We haven't ever seen that happen.
Okay. I actually wanted to ask a question myself. You mentioned there are comets which comes from far away following hyperbolic pathway, and that pathway means they come only once and never return. Is it more difficult to observe those? Are they extremely rare?
Andrei, we've only discovered 2 objects on hyperbolic orbits. One was an asteroid, and the second, Oumuamua, was an asteroid, and Borisov was a comet.
So they're extremely rare.
They are, but there's no trouble observing them. Borisov was easy to observe, but the orbit was easy to map out. And when the orbit was mapped out, it clearly was hyperbolic, meaning that the comet was moving at far more than escape velocity from the sun, and it wasn't coming back again. And so that means it came from somewhere outside the solar system and had a good speed when it finally fell in towards the sun.
Right. And historically, there were no records of anything else hyperbolically, like in old days, right?
People couldn't do those orbits until just the last couple centuries.
Okay.
So, yeah, we haven't been doing it.
Right. Okay. There is another question again from Timur. Is there a way to predict when a certain comet will get broken up by sun based on its estimated mass?
Not really, Timur. Yeah, I mean, you could make some estimates based on how close it's coming to the sun. People for this comet next week could see how close its perihelion was and said there was a good chance it would break up. And that was an educated guess, knowing how hot it had to get getting that close to the sun. But not knowing how rigid the rock is, not knowing what the consistency is completely, it wasn't predictable. And we don't yet know that it actually broke up. Stay tuned next week. Maybe it'll make it through.
Right. Okay. I see another question from AC. Since the ratio D to H in cometary water has been shown to vary between 1 and 3 times the Earth ocean value, in Oort cloud and just a second, in Oort cloud and Jupiter family from the Kuiper belt, this implies small Earth H2O.
Okay, let me explain what AC's statement was in question. His D to H ratio was referring to heavy water, which instead of being hydrogen and 2 oxygens is a heavy hydrogen deuterium, which also has a neutron in its nucleus, not just a proton. And heavy hydrogen and, heavy water with a deuterium instead of a hydrogen and normal water are distinguishable. And what AC was saying is it looks like from the comets in the outer solar system that the deuterium ratio is not the same as in the sea on the Earth, and that would lead you to conclude that not so much of the water on the Earth came from comets. I think that's a reasonable statement, AC, but I wouldn't say that that's completely certain. That's a still active research subject, still discussed, but it is interesting that we maybe can distinguish Kuiper belt objects from Oort cloud objects based on deuterium ratios and compare that to Earth water. It's a good point.
Right.
Thank you.
Thank you. Thank you very much, both Don and AC. And I see that we now approached our end of chat time. Apologies again for a bit unstable connection, but we made it. And I thank everyone who came to this Astro-Chat. I thank Don very much for keeping these Astro-Chats coming. And we hope to see everyone again in the near future. And don't forget to subscribe to this channel. It will help you receive a notification faster. Thank you, everyone.
Thanks, everyone, for coming. Good night.